In this video, we're going to get started with discussing specific industries on soil materials and minerals. Usually we find elements in different forms, ranging from pure elements for precious elements like silver, gold, copper, palladium, platinum. However, the majority of metals exist in the form of compounds, mostly oxides, along with carbonates, sulfates, silicates, sulfides, and sulfates. So we're going to get started with the industries based on the industries that are based on using the minerals in their raw forms, specifically oxide industries. Different oxides have different industrial applications that depends on their properties, their hardness, their optical, magnetic, and conductive properties. Alumina, for example, which is aluminum oxide, is used for cutting tools, sandblasting, and heat resistance materials and bearings. Silica is used as a drying agent for food industries and in coatings and toothpaste as fillers. Other oxides are used based on their conductivity and magnetism and semiconducting properties. Specifically, titanium oxides are semiconductors that are used in gas sensors and electrodes. Other mixed oxides exhibit superconductivity and used in electricity transport and electromagnets. There are typical properties for oxides of interest, starting from the size and shape of the powder. So the size of the particles in the oxide manufacturing vary from tenths of nanometers up to hundreds of microns. And that will affect the properties and the application. So nanopowders, or more generally nanostructures, will have at least 2 dimensions below 10 nanometers. And submicronic sizes are ranging from 100 nanometers to 1 micrometer, and micrometric sizes range from 1 micrometer to 10 micrometer, and then the raw powders are typically in the size greater than 10 micrometer. Measuring sizes depend on a couple of techniques, starting from light diffracting devices, usually lasers. These sizes depend on the diffraction of light by the particles, and the diffraction angles in this case will depend on the particle size, allowing us to determine the actual size of the particles. We also have techniques based on light intensity fluctuation or dynamic light scattering techniques that uses the diffusion of fine particles, usually smaller than 5 micrometer, and their scattering of light. And depending on the frequency of the fluctuation, we can determine the particle size. And the last technique to determine the particle size is image analysis using scanning electron microscopes and scanning tunneling microscopes, and this is typically used for nanopowders. The second characterization of interest for oxides is the chemical composition, determining the exact percentage of each element in the oxide. For composition determination, we usually need elemental analysis techniques, starting from inductively coupled plasma emission or ICPES. That type of spectroscopy will give you the exact mass percent of each element in the composition of your oxide. We also have X-ray fluorescence techniques to identify the type of element in your oxide and the amount. We also have X-ray photoelectron spectroscopy, XPS, and that is really helpful in determining the type, the amount, and even the oxidation state of the metal in your oxide. In terms of composition, we usually are interested in the phase analysis that determines the crystallographic phase of your oxide using X-ray crystallographic diffraction techniques, XRD, either powder XRD or single crystal XRD. An example for that is titanium oxide that usually exists in 2 crystallographic phases that has to do with the different connectivities between the titanium and oxygen atoms in the structure, which leads to a significant difference in the properties, specifically in electroconductivity, depending on the phase. We have different preparative approaches. First one starts from a non-oxide raw material and perform an oxidation reaction. Expose your raw material to oxygen to transform metal salt to an oxide. And typically, these types of approaches are used for obtaining very high purity oxides. The second approach is hydrolysis, in which you start from a non-oxide starting material and hydrolyze it with water to get the oxide, the corresponding oxide. And then we have the coupled reactions, in which you use 2 types of elementary reactions to obtain the oxide. You start a reduction reaction to obtain water in the reaction medium, and then use this water in the hydrolysis step to obtain the oxide. We're going to focus on one example of industrial important oxide, which is titanium oxide. It's used in paints and coatings, in manufacture of plastics, rubber, paper, inks, textiles, and so on. And it's also used as a filler for inorganic sunscreens to block ultraviolet light in this case. The most common mineral for titanium oxide in nature is ilmenite, which is a metal titanate salt that occurs naturally, that contains between 40 to 60% titanium oxide mixed with other metals oxides, mainly iron oxide. The iron that is contained in that mineral is largely reduced with carbon to the metal to get rid of it before you start processing the raw material to obtain titanium oxide. And that's what we will see in specific details later. The second form in nature for titanium oxide is rutile, which is extracted as pure titanium oxide with almost 90 to 98% titanium oxide in the form of sedimentary rocks in rivers and dunes. Let's start with discussing the production of titanium oxide from ilmenite. So you start with the roasted ore that contains low percentages of titanium oxide, mix it with coal, and in this case, coal will, at high temperature, will allow you to reduce the iron oxide content, which will be heavier, so it will sink in the bottom. So you can take that fraction as molten iron and use it to produce different types of iron and steel making. Then the titanium slag will be lighter, so it will float. So you can take it and process it for the next step to produce titanium oxide. Put it through several steps of sizing and crushing and drying to get it to the right size for the next step of production. If your raw material is rutile, you will take the raw material itself and take it through steps of sizing the product, through crushing, grinding, screening, and then drying and roasting the product. And finally, put it through a magnetic separation step to make sure that you get rid of any iron content. And finally, you will obtain a roasted ore with higher than 40% titanium oxide content. Second step is going to be production step. And in that step, we will have different techniques for production. The first technique is called the sulfate process, and this is typically used for producing titanium oxide from ilmenite. In this case, you will take the finely ground raw materials and digest it with concentrated sulfuric acid. The sulfuric acid will dissolve iron content into iron sulfate and the titanium content into titanium sulfate. And to prevent the co-precipitation of iron-3 ions during the hydrolysis, typically we add titanium-3 solutions or elemental iron to reduce all the iron content in your reaction mixture to iron-2 so it doesn't co-precipitate during the second step. And the second step is going to be taking that solution and allow it to stand to remove any insoluble particles, then evaporate it to first crystallize the iron-2 sulfate heptahydrate to get rid of all the iron content, and that can be sold as a byproduct. After you remove all the iron sulfate salt, you take the titanium sulfate solution and hydrolyze it by feeding it in steam at temperature between 95 and 110 degrees. And sometimes it helps to introduce some titanium oxide seed crystals to trigger the precipitation step. During that step, a hydrolysis reaction will take place where the titanium oxide sulfate will get hydrolyzed to titanium oxide hydrate and produce sulfuric acid. Once you precipitate that titanium oxide product, you can wash it and then treat it with titanium-3 solution to remove any heavy elements like iron, chromium, manganese, or vanadium to make sure that your product is pure and remove any possibility for color in your product. The next step is going to be treating the product with alkali metal compounds or phosphoric acid to determine what type of phase you will obtain. If you use alkali metal compounds, you will get anatase crystallographic form of the titanium oxide. If you use phosphoric acid, you will get rutile instead. After that treatment step, you put the product into a calcination step to completely dry it and remove any remaining sulfuric acid or water. That calciner is a rotating cylinder in which the titanium oxide passes through at temperatures from 300 degrees Celsius to over 1,000 degrees at the end of the calcination step. Depending on the temperature, you will control what type of crystallographic form you obtain. If you want anatase, you usually want to keep the temperature between 800 and 850 degrees. If you want to obtain rutile instead, you need to raise it to 9 to 950 degrees Celsius. Once a product is formed, you will put it through milling to control the particle size in the product to a certain range, depending on the application that you want to use it for. And you typically, if it's used in paints and coatings, it typically needs to be within the range of 200 to 300 nanometer with a narrow distribution to ensure best opacity or hiding power as a pigment. After that, you will put the product into a treatment and doping to improve the product resistance to weather, specifically its resistance to UV absorption. So you need to mix it with alumina or silica to protect the product against UV decomposition and give it better mixing in water-based paints. This flow chart here summarizes the whole process, starting from the ilmenite slag raw material, which gets digested with sulfuric acid, will convert ilmenite into a mixture of titanium sulfate and iron sulfate. You will put scrap iron into the mixture to ensure reduction of iron to iron 2, then allow it to stand to remove any insoluble materials, and then crystallize iron sulfate in a crystallization step to remove all the iron content, and finally hydrolyze the remaining titanium sulfate to titanium oxide using water and seed titanium oxide nuclei, filter the product, wash it, and then calcinate it at the right temperature after treatment with either alkali metal salts or phosphoric acid to control the phase that you will obtain. And finally, finish it to the right size and the right size distribution, depending on the application you need to use it for. Alternatively, that production could be done using the chloride process. So in that process, the feed is dried, mixed with coke, and fed into a fluidized bed chlorinator, where chlorine gas is introduced through the bottom to convert the titanium oxide corrode material into titanium chloride. And that chlorination step is going to take place around 900 degrees Celsius. Any impurities of calcium, magnesium, chromium, and vanadium are going to be problematic because both calcium and magnesium will produce liquid impurities of magnesium chloride and calcium chloride, and chromium, vanadium would colorize the product, which should be avoided. So the starting material has to be purified, and any traces of these impurities has to be removed before the chlorination step. After the chlorination step, a condensation step takes place in which the gas stream from the chlorinator is cooled below 300 degrees to separate impurity chlorides from titanium chlorides by condensation, and the exhaust gases, which will contain carbon monoxide, carbon dioxide, and nitrogen, will be scrubbed using water and caustic solutions. Finally, the titanium chloride will be reacted with oxygen at between 900 and 1400 degrees Celsius to form titanium oxide solids that will deposit in this case. So in this step, aluminum chloride is added to catalyze the formation of rutile, and alternatively, we can use phosphorus trichloride or silicon tetrachloride to obtain anatase. The chlorine gas that forms during this oxidation reaction can be recycled and used in the chlorination step in the beginning of the process. This is a flow chart that summarizes the chloride process, starting from the raw material, which goes through a chlorination step by mixing with coke and chlorine to produce titanium tetrachloride and other chloride impurities that can be removed through a condensation step. And the titanium tetrachloride stream is oxidized with oxygen along with additives to control the phase obtained, forming the solid titanium oxide that can be cooled, degassed, and separated, and then finished to the right size in the product. The third process is the CTL process, which is owned by the Canadian Titanium Limited Company. And that process is based on the chloride metallurgy. It has the advantage of the ability to use low-grade ores and ores containing magnesium, vanadium, or chromium. That process is based on the higher solubility of metal chlorides than sulfates, which enhances the leachability of minerals into chloride solutions. A hydrochloric acid is used as the leaching system because it allows for regeneration of the acid by pyrohydrolysis. And also the efficiency of the leaching is improved by the presence of magnesium dichloride, which enhances the activity of the hydrogen ion in the acidic medium by orders of magnitude. Leaching step is started by leaching the crushed ground ore material in mixed chloride reagent that consists of hydrochloric acid with magnesium dichloride, which brings all the metals, iron, titanium, and other metals into solution as chlorides. That step requires 12 normal HCl, but adding magnesium dichloride allows using 6 normal HCl because it actually increases the activity of the hydrogen ion in the solution to be equivalent to 12 normal HCl. And that very high normality is to ensure that titanium species exists in the right chloride species for the next step. The solution has to undergo an iron solvent extraction step first. So iron is going to be extracted with a soluble reagent, which is usually a mixture of ketones and amines. That reagent that extracts iron will be stripped from the organic phase, and the regenerated organic reagent can be recycled to extract more iron. The iron containing aqueous phase can be converted into iron oxide and 6 normal HCl solution by pyrohydrolysis, which allows us to regenerate HCl, and that regenerated HCl can be recycled and used in the leaching step one more time. And the iron oxide hematite produced in this step is actually very pure and can be used for pigment, so it can be sold separately. After removing iron from the solution can undergo a titanium solvent extraction, in which titanium species is extracted from the raffinate of iron solvent extraction. So we have different extractants with selectivity to titanium with these compositions right here that are based on phosphoric acid esters. After extracting titanium species from the solution, the titanium-rich solution is stripped, then heated to around 95 degrees Celsius to produce titanium oxide hydrate, which has the advantage of having a very uniform particle size between 200 and 300 nanometer range, which is very suitable for pigment application. And the acid produced during this step can be recycled into the leaching step. So we saw in that process a lot of advantages, including the high purity of the product and the very good size distribution, as well as the very economically efficient steps of the process itself. So choosing the processes is going to depend on several factors, including the type of raw material that you will use and the economics of the process. If you have a rutile starting material, this is typically very pure, however, it's very high cost. And being very pure allows it to be used directly in the chloride process, which requires high purity, since the impurities of other metals would compromise the process itself and would colorize the product. If you have ilmenite concentrates, which is typically low cost because it has low content of titanium in it, and depending on the concentration of titanium, if it's higher than 50%, you can treat it to enrich the starting material to higher content of titanium and then use it in the chloride process. If it's lower than 50%, it's going to be more economic to use it in the sulfate process, which is not as sensitive to impurities. For much lower titanium concentrations, the CTL process is actually much more advantageous because it's much more economic, it's much less sensitive to impurities, and it produces much higher purity in your product. This table summarizes the advantages and disadvantages of each one of these processes. Chloride usually uses very high purity starting materials, which are typically very high in cost as well. However, the product that it produces is very high purity as well, which makes it of very high value. The cost for the infrastructure is high. However, it has the advantage of medium environmental challenges in terms of the byproducts that it produces. The process is very limited because of the sensitivity to any impurities of calcium, chromium, manganese, magnesium, or vanadium, and it requires very high temperature. Typically, the chlorination step needs to be between 800 and 1,000 degrees Celsius. And this process is currently in use in a lot of production plants all over the world. The main environmental challenges are the disposal of iron and other byproduct chlorides that will form during the production. And the safety requirements are going to be typically high because of the toxicity of chlorine at high temperatures, which is very corrosive and very toxic. Sulfate process, on the other hand, uses very low cost raw materials based on ilmenite, which are much lower cost. However, the product has lower value, and the infrastructure needed for that process are medium cost. However, on the other hand, environmental challenges are much higher compared to the chloride process because you need to dispose large amounts of iron sulfate byproduct and dilute acid that cannot be recycled. The limitations are a little bit less because it's not as sensitive to impurities as the chloride process. And also the temperature needed for the process is much lower, which reduces the cost for production. And in terms of the safety requirements, they're still high because of the high temperature and the acid used in digestion. The new process, the CTL process, uses the lowest cost raw materials, ilmenites with much lower titanium oxide content. And the product is much higher in value because it's higher purity and much better size distribution. The infrastructure needed for that process is much lower compared to the other two processes. It's much more environmentally friendly because it doesn't produce a lot of hazardous byproduct. Limitations are much less. It's not as sensitive as the other two processes, and it uses much lower low temperature and atmospheric pressure for leaching. The leaching takes place at around 70 degrees Celsius, and the precipitation takes place at around 90 degrees Celsius. And in terms of the environmental challenges, as we said, it's much more environmentally friendly because it produces only iron oxide byproducts, which are not as hazardous as the other two processes, and it actually can be used as a byproduct and can be sold. Safety requirements are not much because it uses low temperature and there is no pressurized vessels or acids.